Let's see one example. Loads as shown on the truss, and we're looking for the force in members KJ, KD, and CD. So only 3 members. That means we don't have to do the method of joints. We can use method of sections. So the plan will be we're going to run an imaginary cut through the members we're working with, and then we need to decide which segment are we going to use, left or right. So in this problem, no matter which segment we're going to choose, we have to solve for the support reactions. After we choose the section or segment we are going to work with, we need to draw the free body diagram and place the support reactions on that free body diagram and the internal reactions exposed as externals. Then we're going to apply the equations of equilibrium to solve for the forces. So first I run an imaginary cut through the members we're looking for, KJ, KD, and CD. And then I need to decide which segment am I going to choose, left or right. And now if we take a look at the support reactions, because we realize that no matter which segment we're going to choose, we need to solve for the support reactions anyways. But if we compare the left and right segment, first of all, the support reactions, if we choose the left segment, there are 2 support reactions at pin A. But if we choose the right segment, there is only 1 support reactions. And now, if we also take a look at the applied forces, at the left segment, we have 2 applied forces, but the right segment, we just have 1. So think about when you write the equilibrium equations, do you want to see more forces appeared in your equilibrium equation, or do you rather have none forces in your equilibrium equation, or just 1 force in your equilibrium equation? Well, the answer should be we want to have less forces, right? Then your equilibrium equation will be much simpler. Plus, no matter which segment we choose, we always have 3 and no forces. Therefore, I will choose right segment with the less number of forces. Okay, so the second step is we're going to look for the support reactions. To find the support reaction at pin G, there's only 1 support, which is GY, and we need to use the free body diagram of the entire truss. Again, we're not looking at the details within the truss member. No matter what happens in other places, we just need to see the outline of this entire truss and then check the forces applied onto the truss, and don't think about anything inside the truss, because free body diagram is all about external forces. We don't have to consider any internal forces. So to find the moment, or to find the support reaction at G, GY, the easiest equation we're going to use will be the moment about A. Since at point A there are 2 unknown forces, if we use moment of A, then those 2 forces will not be in the equation at all. So moment positive is counterclockwise as positive moment about point A. So use that equation, we can solve GY, which will be 33.33 kilonewton. Step 3, let's draw the free body diagram of the right segment. So we already solved the support reaction at pin G, which is 33.33 kilonewton. So we're going to draw it here, or put it here. And next we're going to draw the internal reactions, or the reactions we are looking for. But now, after the cut, they will become externals. So first is the KJ. The force will be along this KG member, And for those end forces, let's assume all of the forces are in tension. So we're pulling away from the member. And this is the force FKJ. And next will be the force KD. Same idea, it's along the member. And we'll assume it is in tension as well. And the third one is FCD. It's along the direction member CD. Also, we assume it is in tension. So this is FCD. So my suggestion here is, again, we're going to assume all the end forces in tension. If it's solved to be a positive value, then that means this member is in tension. But if the number is in negative, then that means this member is in compression. So it's easier to handle at the end. And another thing we need to realize is the concurrent. Two forces are concurrent about 1 point, or joint. Their line of actions will be intercepts at 1 point. So for the CD, KD and KJ by the name, right, they will concurrent about point K. So I'm going to put that point, extend the force a little bit, and mark this point is K. And same idea, the CD and KD force, they are concurrent. If we extend the force, line of actions, they are concurrent about this point D. Okay, so we do that for a reason. You will see it when we see the equilibrium equations. Another thing is the orientation of this member KD. The angle phi is given here, or is noted here, but we don't need to, or we don't have to use this angle phi. Instead, if you check the geometry of the truss, this triangle KCD, this bottom is 2 meters and the height is 3. So we have this again, the famous 4-3. No, not 4 here. Sorry, it's 2-3, and then you can have the other side actually. So my point here is you don't have to use the angle, but you can use the slope triangle. So one side is 2, one side is 3. So the other side is the square root of 4 plus 9, which is 13. So we can use the ratio of those similar triangles to find the relation of the KD, of the X and Y component of this KD force. Another thing, don't forget, is the XY axis, because we need to use it for our equilibrium equations. Okay, so I think the free body diagram of the right segment is completed now. So the next step is we're going to write the equations of equilibrium to find those 3 unknowns. So this becomes a 2D rigid body equilibrium problem, and we have 3 unknowns. We should have enough equation to solve for the 3 unknowns. And the first equation I'm going to choose will be a moment equation, because that's the reason why we find those points, point K and point D. Since the force Kj and Kd are concurrent about point K, so if we are going to write the first equation, let me use a different order. Equation 1 will be the moment about point K, because if you choose that equation, the Fkj and Fkd will disappear, will not show up in this moment equation, because the moment arm about point K for those 2 forces are 0. It passes through this point. And another point for us to realize is this point K here actually is not on the body, is not on the rigid body. But we can still use it, because the equilibrium condition states that the moment about any point is 0. This any point includes any point on the body or any point outside of the body. Any point in space will work. So that's why we can write the moment about point K is 0 equation. So find the corresponding moment arms for each force. And now we only have 3 forces in this moment about K equation. Of those 3 forces, we only have one unknown, which is FCD. The other 2 is the 40 kilonewton and the support reaction at pin G. Now we can solve this FCD directly, and FCD is solved to be a positive value, which is 62.2 kilonewton. Because it's positive, so we know that must be tension or tensile force. Second equation, we're going to use the same trick. We're going to do the moment about point D, since 2 forces are concurrent about point D. So FKD and FCD will not show up in this moment about D equation. And in fact, this 40 kilonewton is also applied at point D. Therefore, the 40 kilonewton also has a 0 moment about point D. So we only have 2 forces in this equation, and Fkj can be solved directly. And in this case, it's negative 66.6 kilonewton. So it must be in compression since it's a negative value. The last equation, I can choose a moment equation, or I can choose fx equals 0, or I can choose fy equals 0 to solve for the fkd. But fkd, well, take a look at the whole structure. Fkj and fcd, both forces are pointing to the x direction. For the 3 unknown forces, only fkd has a y component. So because of that, I'm going to choose this equation f of y equals to 0. Although kj and cd are already solved in the previous steps, but just in case we may make errors in those calculations. So when we solve fkd, we don't want this force to be dependent on the other 2 forces. So that's why I'm choosing this fy equal to 0. So the y component of fkd will be fkd times 3 over square root of 13. That's the y component of this fkd force. And plus 33.33 at point G minus 40 kilonewton equals to 0. And FKD is solved to be a positive value, 8.05 kilonewton. So it must be in tension. And now this problem is solved. Example 2, we're giving the loads as shown on this simple truss structure. And we're looking for the forces in members ED, EH, and GH. So 3 members. That means we're going to use the method of sections. So first, we're going to run a cut through the members we are solving for, ED, EH, and GH. And then we're going to choose which segment, left or right, we are going to use to solve for the unknowns. So take a quick look and think about which segment are you going to use. And here is my solution. I'm going to use segment on the left. The reason, first, just like the example 1, it has fewer forces applied on it. Second, the support reaction at pin F, there is only 1 support, whereas at pin A, there are 2 support reactions. So overall, we have fewer forces on the left segment. So we're going to draw the free body diagram of the left segment with the internal forces exposed as externals. Then we're going to write the equations of equilibrium to solve for the unknowns. The first step is to determine the support reactions at point F by drawing the free body diagram of the entire truss. So for the entire truss, we have 1, 2, 3, 4, 4 given forces, and there are 1, 2, 3 unknown forces. But again, since we're going to choose the left segment, so we don't have to solve the support reactions at pin A, therefore we're going to use the moment about point A. And in this equation, we only have one unknown forces, which is the Fy. So this is a rigid body equilibrium problem. And Fy is solved to be 57.5 kilonewton. Step, we're going to analyze the left segment. So draw the free body diagram of the left segment. At the cut, those internal reactions will be exposed as externals, and those are the values we're looking for. Before we know the directions and the magnitude of those forces, we assume all the forces are tension or tensile force, so we'll pull away from the member along the direction of the members. We have FED along the ED member, we have FEH along the EH member, and also note that the FED and FEH are concurrent about point E. The member GH has a force FGH. And also, if we extend the force FEH further down, or if you check the original truss structure, those two members are joined at pin H. Well, we can also tell from the name of the forces. There is a concurrent point H. And also don't forget the support reaction at pin F, which we already solved in step 1. So now we can solve for the three unknowns with equilibrium equations. So the first equation we're going to choose will be the moment about point E. Since FED and EH are concurrent about point E, so if we choose that equation, those two forces will not be in this equation, so the only one force will be FGH. And it's solved to be a positive value, 76.7 kilonewton, which means it's in tension. And the second equation, you can choose either one, just like example 1. We can use the moment about point H, or we can write the force equation. So let's start with the force Fy equal to 0. Because of all the three unknown forces, only this FEH has a y component. So if we write Fy equation, then the only unknown force or only unknown in this equation will be FEH. Again, ED and GH, all of the forces are in the x direction only. And FEH is solved to be 29.2 kilonewton, which is also in tension. And the last equation we're going to write will be the moment about point H. Find the moment arms of the corresponding forces, and there is only one force, unknown force in this equation as well, because the force FGH and FEH are concurrent about this point H, so they will not be in the equation. And FED is solved to be a negative force, which means it's opposite of our assumption, that therefore it must be a compression. So this problem is solved.